Okay.
So we are ready. 1, 2, 3. Hello, everyone. Welcome to this sixth COT music seminar. This seminar has been going for 3 months already, and we are exploring the formalism of reaction networks and ideas related to it, such as self-organization and autopoiesis, to the possibility, the relations to the possibility to understand better musical notions, such as how to generate music or how to represent beauty. Before we start with the talk, Carsten, I would like to take 1 minute to say to everyone that the Professor Humberto Maturana passed away yesterday. I'm not sure if the news are already in Europe, but he was 92 years old, very active, and all of a sudden he got, I think, what I heard is a heart attack, and passed away. So Humberto Maturana is one of the main figures around the cybernetic approach to self-organization. He developed the notion of autopoiesis, which is uh, one of the main notions that have us here talking today. So I just wanted to say that this is a very how, I mean, it was a big impact for all the community here in Chile, because he is Chilean as well as me, and so yeah, we just want to share this and say, well, we must continue his legacy, um, exploring and having the all the fun we have doing this. So nothing sad, just it's part of the cycle. He told us, he taught that to us. So okay, with this we can start the talk, today's talk. The name of the talk is From Data to Music and Back. And the speaker is Carsten Heisterkamp,
Yes.
who is an independent user experience designer with over 20 years of professional experience, worked with and for international companies of the tech industry. Besides his main interests as a critical technologist, more interests lie in the use of code and technology as a means of artistic expression and technological emancipation. He teaches creative coding at the University of Applied Science in Düsseldorf and has a musical background in drumming, music like coding, analog and digital sound synthesis, and digital music production. So, welcome, Karsten, and please start your talk. We are eager to see. Thank you.
Okay. Yeah, many thanks for your introduction. And I feel very honored to be invited to this talk and in this constellation. It's a really, I'm very happy to join you, and hopefully I will be able to present you some new information or from or a different perspective. And I try to share my screen now. Just a second. Um, which screen is it? This one. So ideally, you should see my screen now. And I hope these noises are not from my microphone. There are some noises in the background. I don't know. And I will just start with the presentation, which I prepared for this talk in the last weeks, more or less in my spare time. And it's called From Data to Music and Back, Sonification and Music from the UX Design Perspective, which is my profession, UX design. So this is one topic of this talk. Some words about myself. We just heard it in the introduction. I think I don't need to add much more to this. but I'm not, yeah, I have some musical training, but I'm not, I would not call myself a musician in the professional term or with a professional musical background, but I'm doing a lot of art or musical art in conjunction with others, like you can see in the pictures of the performances together with other artists, or live coding, music live coding with special programming languages for live coding, and also some installations, which is, for example, on the right bottom, it's a generative music piece, which is taking place over a whole day, and it's a 6-channel installation with, yeah, it's sounds modulating the sounds of the architecture are fed back, for example, into the visuals. So it's some kind of strange mix, but I'm also not an artist or a musician. I'm really have a background in design and user experience design, and this is just my, I would say, hobby. Okay. So it's called From Data to Music and Back, and it's at the beginning, it's very much about sonification. It's very packed with information about sonification. The reason is, when I joined the recent talks, we talked a lot about musical theories and sonification, somehow mixed but never really defined what we meant with sonification. And the idea was, or is, to clarify a little bit what sonification actually is. Then we can maybe clarify how we see sonification and in relation to music, for example. And the second part is a slightly experimental, or it's some kind of my take onto the topic, which might not 100% fit into the, yeah, we will see. It's a little bit experimental, and I will present you some kind of idea how I would like to do some research on this topic. So it's very packed. So maybe you ask if something is really not understandable, then you can interrupt me. But ideally, I would answer all the questions at the end. But as I said, if there's something that you really don't understand, or something we need to and that needs to be clarified immediately, we can clarify it immediately. Okay. So sonification in UX design is quite clearly defined. The user experience means the experience of a product or a digital object or anything that you can interact with, and the whole experience can be designed or is designed in user experience design. It's logic, structure, navigation, accessibility. So that's the fundament of what I'm talking now. It's the user experience. User interface is one part of the user experience. And this is divided, for example, in the graphical user interface, in a sonic user interface, and that's what we are basically talking about here. It's an auditory display. That means some kind of technical display that, yeah, it's like a visual display, like the monitor. You also have an audio display, a technical apparatus, which is creating the sounds. It is not necessarily some kind of speakers. It can also be other technical installations. And user experience design finally creates a whole experience. It's always from the user perspective. That means it's user-centric, it's user goal-driven. We always think about from a certain things about from the user perspective and the goals that the user wants to achieve. And the user experience design takes the whole, it's very holistic, and it's not only the user interface, it's also how the overall communication and interaction with an object or a product or whatever, a service, can also be a service, is. And that's what user experience designer designed, basically. Some kind of industry design for digital products. Sonification has a clear place in the user experience design. That means it's usually a multidisciplinary activity between engineering and designers, musicians also. Sounds are used to convey feedback about states, processes, and events of an object, of a product, etc. It enhances accessibility of abstract and non-haptic interfaces or data. That means when we interact with for example, our iPhone or some kind of abstract data, it's usually very hard the concepts are often hard to understand, and we need to, because they're abstract, and we need to make them accessible. So this abstraction needs to be somehow managed to make things and data accessible. Sonification provides auditory support of the sense-making processes. That means we create sounds that make virtual or digital products more understandable, and especially the interaction with these products. Also, important part, it encourages exploration and curiosity. So it's also should be fun to work with, even with data. Yeah, and for sure, for people, for example, with a vision impairment, they need some kind of auditory help to interact with objects. And yeah, so it's getting more learnable, memorizable, and yeah, it's a nicer user experience. Finally, so sonification creates a more or a better user interaction, because it's not always the graphical user interface that's important. It's also the whole auditory impression that you have often and immersion of product. Best example, who would have guessed? It's the Apple product world, especially the mobile. I'm not an Apple fanboy. It's just a lot of things are really very good realized in Apple products. And as you can see here, this is from the Apple Developer Conference, that audio is has the same status, and it's important for the Apple products, like the visual design. And what's in addition is the haptic design. That means, so the vibrations and stuff like that. When you have a new iPhone, it even gives you vibration feedback when you do certain actions on the user interface. And so you create really, so basically it's really just a flat product, but you get in some kind of feedback in for all senses, and the audio is plays one important role in this. Sonification in data science is a little bit different. So what we have seen now is really what we have seen before is really like creating a haptic interface with auditory interaction and feedback. In data science, it's a little bit different. For sure, we also have interaction with data, or can have interaction with data, or have it all the time. But sonification data science means usually that you explore data and analyze data with the oral sense. So you listen to data, basically, to gain insights into data and its structure, and its adds dimensions to the display of the analysis. Because the human auditory system works in 360 degrees, we are very sensitive to timbre, pattern, and volume. So this helps us to find certain patterns in data sometimes. Also, it adds well, Solidification in data science should add value to the understanding of conventional data analysis. So that means when you have your Excel or whatever tool you use for data analysis, and if you are fine with that, there is no reason to do a sonification of data science. But if you hope for additional information because of this special sensitivity of the human auditory system, then you should do, or you can do, or should do a sonification in data science or for your data. But it's often used for promoting, more in a marketing sense, to promoting scientific findings to a broader audience, which is also fine. We will see some examples. I'm not sure if, actually, if Zoom also transmits the sounds that I'm playing, so from the operating system. Maybe it's, so when I play video, I'm not sure if Zoom also transmits the sounds, so we will see later. Yeah, that's, so it's beyond this, it's also used often to get some kind of emotional access or intuitive access to data, so some kind of getting a feeling for the data. And yeah, this is questionable if it's some scientific insight, but that we will see later and discuss later. And here are some examples. I'm not sure if I can play them, or if you can hear them when I play them. So I would like to ask you maybe to listen to them later. I post the link into the chat, maybe, I don't know. But let's continue first, and maybe we can listen to them later. And some of them are in the presentation, and I can play immediately. This one is I think a SoundCloud link, so I cannot play it in the presentation. But what you can see is a very recent example of the Higgs boson data sonified with the Pythagorean harmonics, and the result is on the right side. In the middle, you can see the mapping from the data to the very classical score with the Pythagorean harmonics. So this is very typical that we choose some kind of Western style musical system and map it to a very Western style score, which sounds interesting, but we will see later, or maybe discuss later, if this is always creating insights into the data. So in this case, I guess it's more like for entertainment and marketing. So it's really absolutely okay, it's fine. But the question is, will this produce insights into the Higgs boson data? No. This is another example with a slightly different approach, but in general, it's the same approach. Also here, I will send you all the links later. It's, I'm not sure if you can, I will play this one. I try to play this one. I'm not sure if you can hear them.
We can hear it.
Yeah, cool. So it's a counterpoint. It's called viral counterpoint. And yeah, it's using the counterpoint music formalism, which makes it immediately sound like this and very beautiful and so on. And as you can see, it's a computational algorithm, manifestation, audible, musical representation, and so on. So I just, I think that's enough. So that's a typical example of some kind of sonification, which becomes some kind of musical representation. So I would say it's a musification. And that is, it's beautiful. And yeah, the intention is maybe to make it beautiful. Again, does it create insights into the data? That's the question. So I really like it, but it's always a question of, about the purpose of such a sonification. Here are tons of more examples. They're all, you don't need to read all of this, you can read it later. I will just maybe, they are very, also very recent examples. NASA is doing a lot of sonification and musification. And there's also a record that you can buy where you have the symphonies of the planets, where they sonified the, what was it? Plasma wave antenna, some kind of electromagnetic radiation, I guess. And they call it symphonies of the planets. And it's, what you often can read is something like that it's not silent in space, but it's usually what we will see later. It's an audification of the magnetic field or some kind of radiation, which is brought to the human listening or sound spectrum. So it's usually we would not hear it. So telling something like there is sound in space, it's questionable. But maybe this is also interesting that the comet, which is singing, the singing comet, and this is also audification, means they translating the some kind of radiation into the frequency spectrum that humans can hear. And yeah, it sounds a little bit, you can see the text playing there. It's a unit, it's a sonification definitely of data. And maybe you can get some insights because this was really just translated and not musically interpreted. So I think we will see the differences later. There are more. This is just a quick one. The data sonification. And this is from the images. And it's always interesting to read the descriptions because, yeah, this is also a musical interpretation and experience with other senses, etc. So that is often the background of sonifications and audifications, and not the scientific insight. But what is sonification? There are two different, or yeah, quite different definitions. The one is from Walker and Nees from 2011, so quite young. This is not super interesting for us. It's more a functional definition, but there's also a conceptual definition from De Campo from 2007, a little older, and it divides sonification into three different areas. It's event-based. That's what we've seen with the iPhone, for example. So we are sonifying events and messagings. But there's also the continuous sonification. That's what we've just seen with the singing comet, for example. And there's a very interesting one for us. It's model-based sonification, which I will explain in detail a little, or a bit more in detail. So this is a lot of content. I'm sorry about that, but you don't need to read all of this. It's just, if you check the presentation later, you have some kind of summary of what is meant by event-based. So you have some kind of auditory icons and earcons that we create usually in user experience design. It's like similar to graphical icons. You know all of this from your iPhone, from your operating system. Some kind of, for example, the earcons signify abstract concepts, auditory icons mimic known sounds, like the waste paper bin. When you empty it, it sounds like paper, which on a computer doesn't make sense, but we know that when you hear this paper, it's referencing the waste paper bin in the real world, so we know what it's doing. And for example, if you if you shut down your computer, you hear some kind of music, and this is some kind of earcon for the shutdown of your computer because it's an abstract concept. Then we have the continuous sonification, which is interesting for us already. It's a parameter mapping where I will, which I will explain later also. Then we have the audification. That's basically what we have seen with the singing comet. And real-time auditory monitoring. It's, for example, used in the hospital when you hear the heartbeat sound, which is like a real-time translation of the electromagnetic signal from your heart transferred to an auditory display. And I think these are interesting for us, and all three, but I will explain this later also. Then we have the model-based sonification, which is it's some kind of creating a model. I will explain it later in detail. And the model becomes some single sounding object. So your the sonification becomes some kind of, or the data that you sonify with based on a model will become some kind of musical instrument. We will see later. So parameter mapping I will start with because it's basically what we have already done. And Vincenzo did this, I guess, in his musical interpretation or representation. It's like connecting data to sound via a mapping function and a mapping topology. That means that we try to create some meaningful connection between the data and the sound, and it's called mapping. That means that we change, or if something changes in the sound or in the data, in the data dimension, it's reflected in the acoustic dimension. That is usually done to signify quantitative or qualitative changes in the data to get an insight into the data. And can have discrete and continuous changes. So it means when a certain level is reached, it can be a signal, a sound, but also the reaching, the whole process of reaching a certain level can also sonify it. We can create complex meanings by combining several mappings. We will see also later. And these mappings should convey relationships and correlations. So that's like you do also in standard data analysis. You try to see correlations and relationships. And yeah, it is usually a continuous process of listening, analyzing, and tuning the model, the mapping, sorry. And it's highly effective for multivariate data and sound displays, so we can sonify even complex data structures. And here you see an example of one of my favorite sonification books. It's the Sonification Handbook, which I can recommend everyone who's interested to everyone who's interested in the topic. And here we see some kind of typical mapping that you have. This is a one-to-many mapping. That means you have a data feature on the left side, and you have several data areas, I would say, and you can map it to different sound parameters, sound synthesis parameters. They often use synthesizers and not samples, so that you can really influence certain parameters of the sound, for example. Parameter mapping is often used for musification. What we've heard already, here are some more examples. Very recent example is a neurosynthesizer from Guy Benary, which is he cloned some brain cells, some of his brain cells, and put it into a biological neural network. It's real neural network, and growed it in a petri dish. And yeah, I don't play this because it takes so long. It's a very long video. You can check it later yourself, I guess. It's quite interesting. And he's jamming with his own brain cells, so they're reacting, and it's it's nice storytelling and quite fun. Then we have Yannis Xenakis, for sure. He uses statistic and stochastic processes. I guess you know all of his pieces, and especially this one. And from Larry Austin, who has used traced coastal contours to sonify and create his music. So it's really like an artistic approach, but it's a sonification of data. The model-based sonification, so that was the mapping based, parameter mapping based sonification. The model-based sonification is quite interesting for us, but I'm still thinking about how we can apply this, because we'll see later that COT has some kind of specialties that we need to take care of. That means we have a data space, a model space, and a sound space, and we have the data space as a mathematical space, like vector space. I guess we have it too in our models. And then we have the model space, which describes the dynamics. In this book, again, the example is, for example, a mass spring system. The mass springs are defined in the data space, but the dynamics of the springs and for the simulation is defined in the model space. Then variables are linked and not mapped. They are linked to the sound space. And the sound space is outputting to the perception space. And it's an interactive process. That means we can, it's a simulation. It can be a real-time simulation. And we can, for example, and that reminds me to COT already, add energy to explore the structure of the dynamics of the overall model. And so you can interactively explore the data space by hearing stuff, but also manipulating not the data, but for example, we'll see later, that you can interact and listen into several parts of the data, for example. So by picking certain points in the data and check how it's, how are the data related in a certain area sound like. Data crystallization, particle trajectory, growing neural gas, that are the typical examples for such a sonification. And this growing neural gas, I don't know if you're in artificial intelligence, this is like just how the signal is distributed in a neural network, and you can make it sound. So you can listen to it in real time and check how your model works, your artificial intelligence model works. I've never seen this in real time or in real. It's just, yeah, it's also from the book, but I can imagine how it works. And it's a good example for a model-based sonification, which already reminds me to our problems a little bit. For example, you have the distribution of the signal through the network. You can listen to it on one area or in another area, and you can excite it in one area and listen to it and excite it in the right area, and you can see the curve of excitation or energy over time, and they have a completely different character. And when you excite it on the one, and yeah, so you get used to it, how it sounds, and you can, after a while, somehow explore similarities or differences or how it behaves under certain circumstances. So you can use your oral senses to explore the data. And that's quite interesting because you're playing the data like an instrument. So it's really like picking here and picking there and see how it sounds and how it works. And I think that might be interesting for us, but I'm still thinking about how, and that's maybe something that we can discuss, and maybe it's just one part. So it's, yeah, I think it can be somehow used musically also. And to finish this first part, sound design is in aesthetics and UX design is very important because you don't, you actually want a good user experience, and that so that your products, etc., sound good and nice. And also, when you're working with data, it should not be horrible to listen to. And often you have the case that if you listen to scientific audifications, they're really not very pleasant. So because their focus is really just gaining insights into the data, and the aesthetics are not really important for them. But I guess aesthetics have also in this area, even in scientific precision, can have an or can play an important role because yeah, you have you listen differently to sounds if they sound not nice, but somehow not, they should not sound horrible. But in general, you can say, especially when you're creating sonification for products, that you can follow all the aesthetical rules that you usually follow in all the other design areas or areas of product design, etc., like visual design. You have the same techniques, the same processes. Again, it's a multidisciplinary activity between science, engineering, art, design, and music, and the users for sure, because they are in user experience design. Yeah, they are the focus. And we can also apply design thinking methods and evaluation methods to find out which model works best or which sonification works best and so on. So it's important that the goal of the sonification decides about the aesthetical approach also. And it's always important to tear aesthetics and indexicality. What this means, we will see in the next section. Music for sonification means, or some citation of Ursula Brandstätter of her book Grundfragen der Ästhetik. Music can be described as an abstract language that only rarely makes use of concrete reference and mapping functions. What does it mean? That means basically that we cannot point to something or a person or an object with music. So we always are some kind, always using some kind of abstraction, because music is an abstract language. We always use metaphorical references, so we cannot point to a person, but we can somehow create some musical object that references metaphorical to a person, the king, for example. And it always works with similarities or similarity relationships. Music needs thinking in analogies, has access to sensual knowledge, so it's not, it's a knowledge that we perceive with our senses or learn and save with our senses. Music can stimulate rich sensual experiences and emotions, for sure, and its reception depends on the listening modes, and is open for individual interpretation, which also plays an important part. And it's influenced by culture, knowledge, and conditions. So it's very, it's a very open world that we enter with music. And how can we use it for sonification? And that is one of the questions that came always up when I was listening to our recent talks, is how will we use it, and will we use it for making music, or will we use it for getting insight into the chemical organization theory? Sonification can be used for artistic and musical material. We've seen already the examples where sonification was used for the for making music or some artistic expression. It's often called data art or sound art. But can music be satisfyingly used for sonification? So can we use it vice versa? And when does sonification become music? Can we sonify things, and when do they become music? And can it be used satisfyingly for music? What theories should we use? Traditional or newer music theories, or maybe none of them, just create our own? Does the metaphorical emotional access of music add to the gain in knowledge? Means, can we use emotional access or metaphorical access to gain knowledge of chemical organization theory? That's a more or less a citation from one of the books I read for this. Can music have a meaning beyond itself? Something you can ask. Do we use music as an analytical or an artistic tool, or both? All of them are fine, I guess. Do we want to use COT as a composition technique, or sonify COT, or both? And we are in the middle of the two culture debate with this. So It's what, yeah, the debate between the kind of knowledge science produces and humanities and arts produce. And there's a nice chart in the book, the Sonification Handbook, which divides, or not divides, actually it's like a gradient, two different ways to look at this and to clearly define what is an artistic approach and what is a scientific approach. And means at the right side, we have a tight connection to data, to the data, or with data. We have a lot of artistic constraints on the right side and a high representation of data. Or means the data is very representative in the musification or in the sonification. On the left side, we have no connection with data. We have full artistic freedom and less representation of the data in the music. So maybe it's just using the data as some kind of storytelling, but you are completely free in creating the music and you don't care about the data. And on the right side, you care about the data, a lot about the data, and you are very constrained to it, but musically and artistically. And so you need to decide whether or not you orientate yourself into the right direction or into the left direction. And what came up yesterday, the analytical danger zone, which how I called it, it's in the middle, depending for sure, again, what you want to achieve. And it's always somehow something that you, that we need to define. What is our goal? What do we want to achieve? The analytical danger zone is where it's not clear if you want to have some kind of data-driven sonification or audification, or you want to create art, which is, yeah, so it's some kind of undecided state, and that's hard to maybe, I guess it's hard to for us then, or for an audience, or to what to do with it. And I guess it also creates neither a good sonification nor a good music. So it's in the center, it's dangerous. But also another citation, recognizing in the mimetic sense means noticing the signs of similarities, reading correspondences, and thus discovering the unity of the world. Means the mimetic sense, it's a tool for accessing the world. So music is a tool for accessing the world, even if we work with, not with scientific method, but with similarities and analogical thinking and metaphors, etc. So it's absolutely valid access to the data, in my opinion, something that we can discuss. The third part, and I'm just checking the time, I hope. So it's 6 o'clock, so we are in time. The musical space is the next step that I want to, that is already my experimental approach to this. So we are now leaving the, classical fact-based world into my take on this topic, COT and music. And for the first, I was doing some research on the musical space and how we can get a little bit more flexible in what we are doing. And the musical space, it's also a little bit, or it's my take on what the sound space and musical spaces based on a book, Infinite Music, which I can tell you, will show you later also. In general, sounds or creating sounds means that we are, in its most basic form, create vibrations of atoms in a medium. Today, potentially every sound that we can is possible to create by technology, so there's no limit anymore. We can create highly sophisticated musical or physical sound objects, means instruments, musical instruments. We have technology-wise, we can really define every sonic parameter of a physical object, actually. But we have a lot of sound, analog sound generation technologies, recording, reproduction technologies, and especially in the digital realm of the sound production, we have recording and reproduction and production equipment like sampling, synthesis, additive synthesis, subtractive frequency modulation, phase distortion, sampling, wavetable synthesis, convolution, etc., etc. Physical modeling is very interesting because we can really model physically, and here we have the word model again, physically any parameter, and even on a standard laptop, it's not the problem anymore. Simulating several physically accurate models of some kind of real-world instruments, or even fantastic instruments which obey to the physical laws, but are not met in the real world yet. So you can exaggerate every parameter to on a physical basis to some kind of limits and create fantastic sounds based on physical laws. For example, in Ableton Live, you have a physical modeling synthesizer. In Reactor from Native Instruments, there are thousands of, or not thousands, but hundreds of plugins, etc. So you can really, on a high level, model or simulate physical musical instruments or sonic devices. Composing music means usually music space can be seen as a continuum of free sonic and non-sonic variables. That means we have, if you don't, or in its initial state, the sound space is really pre-quantized, pre-constrained. We did not choose any variable yet and not any value. It's, if you can really see it as some kind of continuum, which is absolutely free at the beginning. Then we start, it's the music space is, the music space is a combination of sonic and non-sonic variables. And it's bigger than the sound space, which is only consisting of sonic variables. I will show you later what this is. It's relating a little bit to John Cage's sound space. And the music space, is who added also non-sonic variables to the sound space. And composing music means creation of musical elements, structures, and meaning by picking sonic variables, like the frequency, for example, we'll see later, and non-sonic variables, which would be some kind of definition of how a musical piece should be played. So it's not a sonic variable, but a non-sonic variable. So if you want to a certain piece, for example, played in a certain environment, which has nothing to do with the sonic qualities, then it's a non-sonic variable, but we will see also later. So then we pick the sonic variables or non-sonic variables, constrain them, means we choose parameters and values. and for example, the length, the frequency, etc. And it's our choices are usually based on intuition, aesthetics, cultural tradition, musical rules, and formal systems. But we've seen, for example, that often we in the Western world choose the Western musical models or systems. And composing is usually a goal-driven activity. So it's the composer has a goal to create a composition, usually. So if you go a step back, the sonic variables, and only the sonic variables are atoms of the music, or you can see them as atoms of the musical space, the building blocks that we use. And so this is a chart I created. It's not my best chart I've ever made. It's quite packed and full, and I need to explain it a little bit. We have sonic or musical variables from the bottom, the elementary level, to the top, to the structured level. And you can see in the middle that we have on the bottom the sound, so in the middle white string, the sound, the structure, piece, instrument, performance, music. So it's getting more structured the higher you get and on the left side, you see that it's a complexity level described. And at the bottom, you have a very elementary complexity, and at the top, you have the really complex variables, which can consist of other variables, more elementary. You can create structures, and by combining variables, and this is actually what we're doing when we're creating music, and that's the whole musical space that we can access, and that's the idea. And we can even define the non-sonic variables. Where is it played, under which conditions should it be played? The score is it's a non-sonic variable, so how it's noted and so on. So that's the whole musical space, and I guess you can study it later in detail. And at the bottom, we have the frequency and the time domain. So it's divided in two domains. And why am I showing this? Because when we already, for example, use some kind of current or recent musical tradition or musical framework that's already existing, or like a Western style or Stockhausen or Schöneberg, etc. Music theory, then they are already bound variables. They are already constrained variables that we use. And maybe it's not ideal to use already constrained variables. Maybe can discuss this later. Maybe it's a little bit hard to understand at the moment. Sonic variables are any attribute of any sound. It's variation over time in measurable values. That's important. And variable plus value is musical information. So maybe it sounds a little bit informatics-like, I don't know, but it's, if you think about it, I think there's a lot of truth in this. Musical pieces can have hundreds of musical variables. They are also, like in a program. From its atomic level to complex musical structures. They are the most elementary musical material, so the sonic variables. Musical notes and score are just symbolic, it's a symbolic representation. And we can constrain them. And when we constrain them, that means, so technically we have no technical constraints anymore. For example, 100 years ago, when we didn't have computers to simulate every kind of sound, You had pianos, you had violins, and the instruments were already constraining the sound. They are like variables. Every music instrument was a combination of constrained musical variables. So you needed to pick what kind of instruments, what kind of material your instrument should be, how many octaves and so on. So you needed to constrain, or in every, still today, every instrument is some kind of constraint of musical variables and combination. And today, with technology, with the help of technology, we can manipulate every aspect and sound on its atomic level. So on the very bottom level of what we have seen before. And the creative process basically means today choosing the right variables, constraining and quantizing these variables in the frequency and the time domain. And that means creating complex structures of quantized musical variables. That sounds very abstract, but I hope you get it. And we use certain rules and principles to do this. And by basically constraining musical variables means picking a variable, assigning a limiting or quantization of its values, organizing them in the time and frequency domain. So it's organization, creating relations. And in our case, COT is, I think, so that's really my take on this, and that's just an idea and that we can think of. And it's really not thought absolutely to the end, because I'm thinking just some weeks about this. And as you know, I'm just, it's just, yeah, something I'm working on. And so that means COT is the main constraining factor in our case. So it's constraining the musical space, the musical variables. That means the constraining by mapping and linking COT variables, depending on what kind of sonification model we use or musification model we use. For example, mapping is the parameter mapping, and linking would be this model-based sonification. And select, organize, and quantize variables in a musical way means indexically low, or indexically high if we really stay close to the data. That's something we need to think of. Sonification for COT and music, and we are close to the end. Sonification for COT and music, I called it COT and musification. And this is, again, very experimental at the moment, something that I'm thinking about, or how I think about this whole topic is the idea of creating yeah, some kind of different take onto this topic. And it's really it's not an easy topic, because for sonification, I think, because the COT modeling framework is an exceptional species. It's a high dynamic system of networks. So it's a very not typical, or not the standard way how to sonify this, because we have a highly dynamic system and not just data. Everything is continuously becoming, so it's change over change. Self-constraining and organizing means if something becomes an organization, it's somehow acting self-constraining. So we have some, speaking of constraining musical variables, we can think of maybe COT is self-constraining musical variables. Structures create structures. So that's, yeah, it's more or less how I see COT at the moment. Mass action kinetics as a not quantized time, I think. I'm not sure about this. Maybe you can tell me later. And we have emergent structures that can show certain behaviors in individual degrees. and they have also properties like can have properties like self-maintenance, resilience, means ability to compensate perturbations, behaviors like buffering, reducing, consume, etc., and goal-directedness. How can we sonify this? So and that's what I'm currently thinking about, and this is a proposal for sure, or how to, where I to put maybe some more thoughts into. First, if we want to sonify or musify the COT framework, we need to think about if you want to use the mapping, the parameter mapping or the modeling model, or something totally different, but I think we can combine, for example, mapping and modeling, or it's an idea. I'm not sure if it works, but the two concepts that I've shown before might be useful. It might be useful to combine them. But first, we need to clarify the goal of the musification and sonification. Again, do we apply music to understand a certain model of which is defined in COT? Is music applied to understand COT itself? Is COT applied to a musical model, for example, to understand music? Or is COT is it a tool for generative music? And what choices are meaningful in terms of the goal of the project, so especially for mapping and modeling the sonification parameters and variables. We had this already, what musical theories should or can we use, or just discard them and create a new domain-specific musical language. And the idea is basically that the COT should create or produce its own musical constraints, which is, I guess, not easy to achieve, but it's just my train of thought at the moment. And for this, we can create some sound species and musical reactions based on the elementary musical variables. Mass action kinetics define the time domain and some kind of fluid musical pulse. Concentrations and coefficients define a fluid time per species and reaction. When do structures emerge that we perceive as musical pattern? Or how do perturbations sound like? How might attractors and dynamics and its dynamic sound? So that's questions that I'm asking myself at the moment. And as I said, it's highly experimental thought at the moment, but I hope it's some kind of useful to think about this. And again, I created another big chart, which I'm not very proud of, but I don't, in this short time, I was playing around of this. And so we have, on the left side, we have the real world, then we have in the middle, the COT space, and on the right side, we have the musical space, and we mapping from the real world into the real world phenomenons into the COT space, and from the COT space into the musical space. I think we're doing this also if you disregard my whole idea of so in general, we need to do this. And so we have some kind of, two-step mapping, and we need to think about the first step, what do we want to model from the real world? And in the second step, how do we map this from the COT space to the music space? And on the top, the blue arrows means how do we interpret this? And as I see it, since we use music it is basically a metaphorical pointer, more or less, when we interpret something like this is a musical pattern, where does it point to? You know, and we'll see it in the next slide. And we are close to the end, so it's at the bottom, it's still the most elementary element. I tried to figure out, somehow create this structure of from the elementary to the structured. And I think there is some way to map this and to or to model this. And this is just my first approach on this. And I would like to simulate this. But these are, I guess, you can check it later in detail. The gist of this is that we have a two-step modeling, if I'm not wrong, from the real-world phenomenon to the COT space, from the COT space to the musical space. And these are all critical mappings. So how we, depending on what we want to create or what we want to learn. And see that we, for example, if you map it from the COT space to the musical space, we can do it free or very formalized, like some kind of musical formalism that is existing. In the middle, it's the free jazz, some kind of somewhere in between. And yeah, on the right side, there's a musical space. So that's basically the idea of this very packed slide. And I hope it's somehow clear what's meant by this. And then I thought about, or in more detail, what could we expect if you do something like this? So it's really, I think it should be something like even a real-time simulation, where we have on the bottom the very elementary entities, again, like from the real world, a distinguishable phenomenon is mapped to an abstract species, and this is mapped to a sound species in this idea. Like same to the process of the real world, to an abstract reaction, to a musical rule that we for sure need somehow define at this elementary level. And then the networks and the combination of musical, the network of phenomenons point to the abstract or map to the abstract reaction network. And this abstract reaction network points to a combination of musical species and rules. And what could we expect, or what does it mean musically? For example, at the bottom, sound species is a distinguishable sound. A musical rule is somehow creating or describing the consumption and production and reproduction of certain musical variables or species. And then the combination of rules and of musical species and rules, the combination of musical species and rules could be imagined, and that's just one interpretation, some kind of generative scales, rhythm, sequences, any change in an elementary variable, musical variable. And then we have the simulation. And when we, so it's just, it's not just depicting again, at the bottom, we have the abstract reaction networks, we have the organizations in the middle, and the meta organizations. So it's really, again, getting more complex the further you get to the top. And for example, from the elementary structures, we create this complex structure, or better they create themselves. And here it's really some kind of diffuse space at the moment area where I'm thinking of. So that's why I created this cloud-like imagery of all the aspects that are involved in such a simulation, like what could appear like self-organization, self-constraining, resilience, so we have concentration somehow in there, the flux, the perturbation, attractors, etc. So it's something that is somehow happening in the simulation and maybe could be sonified. So maybe we can hear attractors in some way. I know what an attractor is, and it's just an idea. So we can even think about sonifying this the state space, for example, of such a simulation. And what can we expect maybe musically is at the bottom, creation of new single sounds, one-shot sequences, scales, because they are not resilient or not really a closed organization. They're just maybe playing once and you would never hear them again. But in an organization, musical organization, it might happen that you can listen to lasting loops of musical pattern or change in a sound property. And one step higher is lasting. So a meta-organization, which consists of a lot of or several musical organizations, can be seen as some kind of self-composing piece. And you can maybe expect something like a lasting new complex musical structures, where I would say it's always also still to define what is meant by musical. And or a combination of looping pattern and changes in sounds, and finally the simulation itself, which is creating the vessel or the workspace and doing all this, calculating more or less all this, what's going on in this, the rules and so on, can be seen like a performance or generative piece and performed by the agents of COT, changing over time, for sure. And that's something that, so time is still a concept in COT, which I'm not fully understanding. I know it's based on the mass action kinetics, but something that I need to clarify for myself more. Then we can expect structures, organizations, and meta-organizations appear and vanish. So some kind of musical pattern appear or stay over time and then vanish. So it's continuous change from the start of the simulation until the end, until we decide somehow, or we can define if there's no structure anymore, then maybe it might end. And we can, one idea is to simulate it, the perturbations interactively, for example. And this is the last slide. So we can add some kind of individual perturbations, each simulation, to see how it reacts. It's like the model-based example where we can excite somehow the system or the model and see how it reacts. And and somehow create attractors with this, maybe in real time or interactively. And and final slide, more or less. How do we simulate this? So some kind of virtual, I'm thinking about a virtual workspace and simulation space, a user interface to interact with the network, for example, for the perturbations done by an external agent like a user. Ideally simulated in real time, web-based or an application. Either if it's computationally too heavy, what I read in the paper, it's very computational, very heavy. Maybe we can, for web representation, just provide some kind of pre-rendered simulation, or simulate but an interactive local application for real-time simulation. I'm currently looking at some kind of or different technologies like Super Collider, Faust, audio frameworks. Open Frameworks is a programming frameworks, framework for C++, creative coding framework, or in Rust, very up-to-date language or very new language, and so on. So it's technical detail. I'm not sure if this is interesting, but just in case you're interested, you can talk about this. Yeah, and finally, so we are close to the end. So it's how do we analyze this, and how do we interpret all of this? We have the same formal problems when interpreting music, like we had when we trying to create mappings, musical mappings. So there needs some kind of formalism, that framework, how we interpret what is a certain pattern in music pointing to, what does it tell us about the data or about the dynamic of the system that we need to define somehow. And so which musical structure or pattern points to what in COT? Which information do we want to get out of it? An idea is to let a trained machine learning model detect the structures, but how do we model and train the machine learning model? We have, again, the same interpretation, and so we need to define very clear what we want to train. Yeah, and it's definitely to be continued. And as a last gimmick or idea is, this is, yeah, it's a work by the Radical Norms Design Agency, and they created some kind of physical construction where they combined some kind of objects on a rotating cage, and it's widely rotating in all directions. And anytime when an artificial intelligence, which is watching or observing this rotating objects, so they created a form language and put it into this cage, which is rotating. I can show you. Anytime or every time when it's very sure that it's a chair, and it's analyzing this rotating object all the time, and sometimes it's because it learned or was trained on chairs, on millions or hundreds, thousands of chairs. At some combination of these forms, it was thinking it is a chair. It was, yeah, accidentally or wrongly thinking it's a chair because it's the same data that a chair produces in a neural network, or the same, yeah, structure of data. And then they took this. Anytime it was the AI was sure that it's a chair, they took a picture of this combination, and then they just rebuild it in physical space in real time, in the real physical space. And the idea transferred to our problem is that we might do something similar in a very artistic way, and let an AI trained on really musical pattern of the existing musical theories listen to the result of the simulation, which might be not musical at all. It might be noise, just noise or strange sounds. And anytime or every time when it's thinking it's some kind of musical pattern, or it detected a musical pattern in this, even accidentally, we can use it for and recreate somehow musically and use it in a similar way like they do with this idea. Yeah, and I think that's it. I don't know how to leave the slide. Thank you very much. I hope you are still all with me. It was a lot of information, and I'm open for discussions and questions now. And I'm very happy if you give about any kind of feedback, because it's really the first time that I did some kind of, or this kind of presentation. So it's really valuable for me if you give me some feedback about this.
Thank you very much, Carsten. To me, at least, I have to say, this was a very, very nice systematization of what we have been discussing so far. So my little comment to say before we start the questions um, is that you were able to put this in a very concrete, systematic framework that we can now start discussing further.
Thank you.
So I think it's really, really now like thinking of how all this have been. It seems that this project is taking shape. So I'm sure Christian, at least, will be glad to comment. And well, let's start with questions. So whoever wants to start can take the lead and say something.
Maybe just to make the discussion more interesting, you could stop sharing the screen so that we can see everybody together on the screen.
Yeah.
Yep.
Okay, so here we are. So any particular questions? I was kind of actually about to ask you, I was thinking of asking you about what you talked by the end about artificial intelligence related to it. So I think, but I wonder if there are some other questions, maybe Francis or whoever.
Well, I agree with Thomas that this is a very systematic overview of all the different issues that have to do with connecting COT with music. Issues in the sense of things you could do, and issues in the sense of questions that you have to answer. But it was maybe a little bit too much, so it may be overwhelming for the people who
What I
have
often hear
deeply about the topic yet. But I think it's, as I said, it's a very nice mapping out of the whole domain. And now we will need to choose some parts of that very big domain to do some experiments with. And yeah, as you indicate, there are many different choices that can be made.
So we are in some kind of mapping dilemma. So mapping what to where and so on. So it's yeah, and it's a super interesting topic, and I really would like to spend more time on this. And let's see.
And there is something I would like to make a comment. Maybe if anybody wants to interrupt me and say something, like, to me it's fine. I'm trying to start a discussion. But one thing I was kind of reflecting while I was watching your simulations, like the idea of simulation is okay. Like, because I'm of course thinking of what we did with Vincenzo a few weeks ago, which was taking directly a reaction network and plotting or not plotting, sonifying the concentration of the molecules or the reaction rates of the reactions over time, and say, well, the mapping was the more concentration, the higher the tone, or the more reactions per time unit, the higher the tone. So that was our direct mapping. So we took the system and we made a direct sonification of it.
But
Now I was,
I'm sorry.
Yeah. Go ahead.
I just wanted to say that you used a certain, for example, a certain musical framework. I think it was Schönberg, when you did the mapping, for example. So you were always already in a kind of musical space defined by someone else. So that's the idea of what I'm thinking about, that if it does make sense, for example, using the Pythagorean space or the Schoenberg space, or yeah, John Cage. I don't know which space.
Yeah, I know this.
Or,
This is a direction.
So
My
we
question
are
doesn't go. It's not on that direction though. My question, I was just summarizing that issue, so people who were not at that talk were kind of with stay with us while we discuss. So okay, that was just a summary, and there were choices that were made, of course, about how the tones were chosen from the concentrate, were mapped to the concentrations and so on. There was a choice, but one of the choices that we made is that we decided to map directly this realm of the chemical model to the sound. But the problem, or the not the problem, but the expansion on the idea is that we as instruments, as people, when I play an instrument, there is something going on in my mind which is not exactly the thing that makes a sound. I do not sound exactly on what my mind is doing. So my mind is maybe thinking of many sounds, but I'm choosing to play one of those sounds, even though I know I could play this or that. When you have a discussion, maybe composing a song or composing a melody, you feel that there might come this or it might come that, right? So there is a sort of um, not direct expression of what it's in your mind. It is first, it's like the chemical soup in your mind, and then the chemical soup kind of collapses to something or makes a decision or something, and that's what then it's played by the body, which is not a direct representation of what's in your mind. So the concept here, just to open the discussion, is that there might be a latent reaction network, a latent system, like a neural network or reaction network or something, that whose outcomes are these elements that we later sonify. It's not that we sonify directly a system. It's a system whose dynamics creates entities which are later on sonified. You see what I mean? So I'm not sure if I saw that in your diagrams. I think I got the impression that maybe because of the generality, we can consider the latent network and the outcomes as one single system. It's okay.
How do latent reaction networks come into existence? How do we define them at the beginning? Or
No, I haven't thought about it. Now I was thinking about it, and I thought that
I think that's for example something for simulation, for some kind of real-time simulation, because it's the same with computer programming. You need to exactly at the beginning know what you want to describe, and you never describe something which is producing something which is not. Well, you always or never leave this framework that you described in the programming language. Even
no, it's completely compatible.
Latent. I'm not, and a latent reaction network would be something emerging or emergent maybe that could emerge in a real-time simulation, especially when you have agents outside of this, like interacting with the simulation, like we have seen in the model-based sonification, where you can excite from the outside, and adding something not predicted or not described in the code or in the model, because it's coming from outside and it's adding something from the outside which is not part of the description in the code, or at least not directly part. For sure,
Or you allowed it to be that way, of course.
And and that's maybe the interest. That's what I was thinking about when I was thinking how I would approach it, and that I always would somehow, maybe it's because also I'm a user experience designer, that I would always make it interactive and not like using the final, or you are using the data that your simulation somehow output it and use this data, which is somehow crystallized and frozen as data, and then you just transfer to musical space defined by someone else. So you could also go and create your own musical framework or theory to map it to. That's the idea. So that we don't map it to Schönberg or to Stockhausen or to any other existing musical framework, I would say, but maybe think about something new there, and which is maybe it's too big also, because we need to think what is music, what is musical, and so on. Maybe it's too huge, this topic, to changing all of this. So it's fine, maybe using the Pythagorean music definition or musical framework, etc. So, but in general, I would say that a real-time simulation would give a lot of insight into this. So it's really exploring the dynamics of the data and of the COT.
Yeah.
And the other one is just sonifying it, which is also fine, but exploring and in this case, I think it's a more, or might give more insights to the COT. Yeah, that's
Yeah, sorry.
I think, Carsten,
Sorry.
it would be interesting to maybe look at more of what I would call the mathematical background of this whole. And like if you talk about Pythagorean or other kind of intonation scales, just look at the ratios, the intervals between different notes. And if you go into that mathematical frame, it would be easy to kind of map more continuous variables and not structured into note scales already. And so you could think about ratios and certain factors of ratios relating to others. And I think it's something that would interest me to think a bit about that, because to get it a little bit more in the microscopics music and not already into that Western tonal scale. And because the risk is always that you will find what you were set out to find in that case. So I think it would be a good idea to take some distance. And I had one question for you, because you have a background also in sonification. Did you watch also? I don't know that much about this, but the relations between sonification and movement of sound. I mean, like if I think about movies that need sound, I think there's a lot of theoretical frameworks about how sounds or how movements through space are related to sound.
Yeah, that's definitely something we can think about. And I think, for example, especially for movies, and usually it's in new movies, it's surround, it's 360 degree. We can use this definitely. But the COT at the moment doesn't have a spatial, you are working on the spatial theory at the moment for COT, Thomas, if I remember it correctly. But you can also, for sure, map it to the spatial 360 degree space. And we are very, so why are we so sensitive to this? Because in the former times when we lived in the forests and even in the trees, we were listening to our family. We knew exactly where our family, for example, is. So we are very sensitive for our tribe, where our tribe is. So we were connected to them via our 360 degree oral senses. So that's the reason why we are sensitive and why it's so emotional when we listen to something. And that is something that we definitely can use. So it's a question if we take the spatial component into account of COT, maybe when it's developed, then I think we have also a tool here to organize it in a special 3-dimensional auditory way. It's super interesting because I like working with multi-channel sound also. So it's
yeah, I have experience also with multi-speaker installations and synthesizers, and also I think there's a strong relationship between musical kind of perception and movement in space.
Yeah,
I think it's interesting.
Absolutely. Yeah.
I would like to do my talk about this afterwards, or some aspects about this.
Yeah.
Maybe just a remark. When I introduced the model that Thomas and I are implementing in our simulation, I referred to Schoenberg. But it's not that Schoenberg used that model. It's just, I mean, we started from his famous sentence in that article, linear counterpoint. And we highlighted the fact that an interpretation of that sentence in the domain of dynamic systems would be very natural. But if you see the work of, I mean, if you analyze the work of Schoenberg, he did not use that method. He created music in a different way. Also, I would like to highlight that we are also experimenting with Pythagorean scales and 31st tone music, which I'm completely unaware of. And it's very new to me, but the thing that we are toying with is not restricted to the Western typical, the Western scale. That's just what I wanted to add.
Yeah, that's so it's also interesting to use several music theories and compare them. What happens if you use the same data in different theories? So it can also create some kind of insight. And so it's absolutely fine. Huh? So it's just that I thought about what does it mean when we already interpret something completely new in some kind of already defined, from someone else defined framework somehow, which is, maybe, which is interesting, definitely, but maybe if it depends on the goal. So, and if you have a goal, to get real insights. I don't know. You in other areas you also use some kind of frameworks, existing frameworks, and so it's fine if you use musical frameworks. It was just my train of thought that it might be distorting the results somehow if you use some kind of existing musical referential space, and maybe it's a good idea to create in some kind of own musical space. So
yeah, certainly true. Also for me, yes.
Well, as somebody here who doesn't have a musical background, I have very little to say about all these different systems of music, but my interest is scientific. That means COT, I kind of understand at a relatively abstract level, and my original motivation for suggesting to put it in music is for us to indeed kind of get a more intuitive understanding of COT, and therefore I would be inclined to say in the choices we make, we should be led by COT. That to say, if we find an organization that is interesting, let's say from a scientific point of view, let's try to find the mapping into music that as much as possible keeps the dynamics and the structure of that organization. So let's not think too much about what precise system of music we want to map into, but let's do it pretty raw, like each species, one type of sound, and then the time dimension becomes a rhythmical dimension. And then if the organization has some interesting inner dynamics, which I would expect, then I would expect that our auditory sense would pick up that dimension. And once we have this auditory sense, maybe of this pattern in time, then maybe we can start to think about fine-tuning the precise mapping, the sonification from species and reactions onto musical sound. But so I would start with try to make a pretty coarse mapping. If it kind of captures the idea of the intrinsic self-organizing pattern, then we know we're on the right way, and then we can start to fine-tune and maybe look at better mappings that are more aesthetic or more pleasing or more fine-grained. So that would be my approach, I'd say.
Yeah, this is what I'm thinking too. What we are discussing a lot in Düsseldorf, and so I think too that Carsten provides us here with a coordinate system with his talk, that we really know where we can position ourselves with our approaches. Is it more towards sonification, which is that what you said, Francis, right now? So keep it close. Let's try really to translate an organization and reaction network, just sonify it, and this is one approach, and the other approach is more artistically. So that, but we always know now, having this coordinate system where we are with our approaches, which is interesting because for the examples, the students, they are also come up with all kinds of different ideas. And we said in our seminar, let's keep it simple at the very beginning. Let's keep it simple, but it's so that's why also why Carsten pointed it out in this rich detailness, because it's really to make clear people who start to work on this how much ideas they already bring in. You know, trying to, because rhythm, for example, is such a complex thing, and to break it down. Just to get a transparency towards an COT model, this is really a demanding task, and this is what we are working on at the moment. But on the other hand, and it's exactly, and I'm also I also have the position that we won't suppress any suggestion or any idea or any association. The important part is that we know where we are within this what concept we are working on. This is the and also but we will maybe I thought that the students maybe in later times when it is more concrete, that they also present their ideas here in this setup, because it's really interesting. And Thomas and Vincenzo, they will join us in 2 weeks' time, that we discuss in a smaller circle the outcomes that we are working on at the moment. Now I lost the plot. Sorry, I don't know what I wanted to say. I lost the plot. But yeah, as I pointed out, this is the important part. Oh yes, I know what I wanted to say, and it's already what we are asking ourselves at the moment is on which level of COT possibilities are we working on at the moment, and we cooked it down to just the relational description level at the moment, you know, and we are still just using the toy model that Thomas and Vincenzo created for their presentation, the five reaction model, because this is complex enough to start with, and this is really that, and another interesting idea to me, what Carsten pointed out, is the question: can we provide people with a tool that they can explore the reaction network? This is a very interesting task. But I think before we can design this, we really have to understand how it works, and we have to start with a very simple sonification. and the mapping possibilities where we can map it to, so that we really get a feeling and the insight, as you said, to make it that an intuitive understanding is possible. This is really not an easy task, but very interesting.
I just found the comments in our Zoom application, and there are also some interesting comments in there from Catherine. Is it pronounced correctly?
Yeah, you got it.
Yeah, maybe you can just summarize it, because I would just read it, because I'm not able to summarize it quickly, but I know what you're talking about. It's very interesting. I think it's an interesting point.
I don't think it's that. I think it's a similar point to ones that you've been making. I just maybe articulated in a slightly different way. I mean, you made the point that we, with contemporary sound making, we have basically, we have infinite ability to play and create. What's that?
It was slightly exaggerated, just to.
Well, yeah, but no, but we do. But the constraints, there's still constraints, and it's true that you don't have to be constrained to a particular musical scale, and you don't have to be constrained to a physical instrument. But we're still constrained by the physics of sound, and we're constrained by the perception, by the assumption that we will be perceiving it through hearing. And I think that those constraints are actually the reasons why it's quite difficult to figure out how to make sonification insightful. That's my own opinion. Having played around with it in a physics context, it's hard to do that, because you have to understand things so well already that the insights may come through figuring that out, but they don't come through the listening. Except while I'm speaking, I will say I really like the idea of exploratory sonification or exploratory interactive simulation or modeling. That seems like it could be really. It seems like it'd be very hard to do, but seems like it could be really exciting.
And that's what you pointed out in your comment, that that it requires knowing about the interesting data features first. So it's and if you, maybe you have some kind of explorational tool that you can figure it out maybe interactively somehow. So that's would be one idea. I don't know.
You still have to design for. I mean, you're always designing for the kinds of things that you think might be interesting to discover, which means you kind of need to know what they are already. And I think that's just kind of the problem in a way with trying to design a representation system in order to discover is a hard thing to do.
Absolutely. Yeah.
Surrounded by chickens here. I'm sorry for the noise in the background.
Yeah, I love your virtual background. It's so realistic.
Nice sonification of the virtual world. Yeah. It's real.
Amazing. Natural sound. Yeah, actually, that was another reflection following what Catherine said, that we are here. That's why I like so much your systematization, because I've been recently discussing about emotions and how to represent or model, or what framework can we have, and so on and so on. And we don't have even words to talk about it. We don't know what are the fundamental processes. We know nothing about it. And we have theories that have dimensions. It depends on this and that. And why this and that, and not rotate to this other and this other, and one not having 3, 4, 7 dimensions. So we are really, really in regarding beauty, creativity, emotions, and so many other fields, or so many other phenomena. We are sort of blind to understand what they are, how to represent them. So that's why my first comment about latent networks was a sort of possible way to model, to have another representation, which is not directly the phenomenon, but another thing with its own properties, with its own structures, which will be models of these features that are inside the mind of a composer. That was my idea saying before. But the good thing of what you do is this systematization is that, as Christian said, that it's kind of letting us know where we are, what we know, and what we don't know, at the moment, but at least we know that it exists. So that's something really important. So there are things we know that we don't know, and there are things that we don't know that we don't know.
Yeah.
So it's good to know what you don't know first. So maybe there might be an indication of advancing on the things that we don't know that we don't know. So yeah, and the exploratory phase, I think it's kind of a corollary of your talk, that the only approach we can follow for the moment is exploratory. We don't even, I was working on a STEAM education paper. Do you know that thing, STEAM?
Yep.
And actually an expert I was having a discussion with yesterday told me, because we are doing a learning model out of this STEAM framework, and he explained me this, so I will share with you. First layer is exploration and manual control. So because this is thought for classroom settings. So you have exploration. I don't know if this word exists. Indagation. Does it exist? No. And let me translate, because I don't know but it's very similar to, it's like collecting facts.
Mm-hmm.
So fact collection, exploration, and manipulation. That's the first. It's very data based. So you only do and take. So the second aspect is relational objectual conceptualization. That's the second layer, where you individuate objects, you individuate relations, and you identify direct causal relationships. That's the second layer. Then the third layer is called cognitive strategic achievement, which is kind of completing the conceptual framework from these fundamental causal relationships. And that's where hypothetical reasoning, creative thought, and analogical reasoning appears. Then after that, you have conceptual understanding, which explains the elaboration of metaphors, problem solving, and conjecture establishment. And finally, you develop an active ecological knowledge, learning, which is critical thinking, symbolic representation, or mathematical modeling, which they like very much in that field, and knowledge transfer to context, to different contexts. So this is a sort of big general mapping of how students learn in an interdisciplinary framework and so on and so forth. And I was now like thinking that we are clearly in the first layer. We have no clue about what are the objects, what are the relations between them, what might be the causal implications of one thing to the other. But at least now, this is a sort of advancement that we should kind of, along this project, provide the tools to explore, fact collect, and manipulate systems. So from the systems, we do this. And I think we should do this like very humbly for as long as needed before these objects and relations become evident. So this is my opinion. Yeah.
I think just one, if the question is, we want to hear, I don't know, dynamics or the structuring of chemical organization theory or networks by music, then in fact the next step should be that we should study the aspects of perception, music perception, how this works, how in fact the ear processes music, because that would deliver us with, I think, the atoms that we need to simulate this process, or to be able to make something relevant. I think that should be an interesting topic still.
I wouldn't say how the ear, but how the brain processes. The
Also.
brain is very good at recognizing patterns, and the patterns, the sound patterns tend to be patterns in time, while the visual patterns tend to be patterns in space. And since COT is intrinsically dynamic, that's why I thought that sound might be an easier way for the brain to find the patterns in the.
Yeah.
And I think that understanding better how the brain recognizes these patterns is also an important step. And I'm looking at some neuroscientific models, the predictive processing and such, that may be relevant in that respect. I don't yet have a concrete proposal, but I think that that is important. If the brain can recognize a pattern in something, then it becomes meaningful and it starts making sense.
And it's, Francis, it's happening really low level. There's the auditory cortex triggered directly in the hearing system. It's a really specific kind of time perception, but it's, to me, it's related to space perception of sound. I mean, the hearing system as a radar, as a kind of echo. Yeah, I talked about this already. If people who are visually impaired, they are able to localize themselves in space with their ears really, really good, really well. I think it's
by the way, a big difference. I think, I'm not sure, but I think
maybe I'll try to talk a bit.
Yeah, I just didn't want to interrupt you. Sorry.
No.
When you because that's a big difference when we let. I think I'm not 100% sure, but if we let some kind of artificial intelligence listen to sound, which is just listening to sound data, it doesn't have this 360-degree aural interface. It's just looking at data. So, and that's a big difference, for example, and which I would like to use. So it's a lack of some kind of discrepancy, how artificial intelligence finds pattern. It's different than we do, especially in the audios, in the sonic space. And it's more or less, it was a creative idea, because Thomas also asked, and it was not clear maybe at the end, some kind of creativity tool. It was just like, it's not a really an analytical tool. It was just more like a creative tool. And like this example with a chair, what would an AI hear, and what do we hear, and what would some kind of artificial intelligence hear? And it would be fun maybe to what the AI regarded as some kind of musical pattern, which was trained on musical pattern for sure before, regard in the sound as pattern, and then just create something out of this. So it was just some kind of inspiration. So it was not really 100% seriously meant. So it's but maybe an interesting approach. So what's the difference between our listening to finding patterns and how artificial intelligence listens and finds pattern?
Well, I liked your idea in the sense that it could be a way of automating the process of finding better representations. Suppose that you have hundreds of parameters that you can vary in your sonification, and you don't want to have people listen to all the different variations to find the best one. You could have an AI that's trained on recognizing musical patterns, listen to all of them, and if the AI thinks it's a musical pattern, then you could ask a human to listen to it and see whether it agrees, whether a human agrees, and yeah.
The classical monitoring job. Yeah. And that's maybe a good application. Yeah. But that's all. These are all ideas I'm currently playing with. So let's see if we can implement something like this.
Yeah. As a last comment, I personally want to say that I see a lot of potential to turn this into a sort of article, document, book, chapter, or something. Like it has the potential. I think your diagrams kind of help a lot to think this can be systematized, this can be explained in following the steps you follow. So I don't know if you in Düsseldorf have plans of a handbook or something like that, but of course it's a lot of work to do that. But at the conceptual level, I think it's not, of course, fully done, complete, but as a introduction, or to, I see clearly that this could be done. So I only mention it. I don't engage myself in proposing to be part of that at the moment. I'm not available, but maybe in the future it could be a good horizon.
Yeah. Some of the illustrations were references from the book, this Sonification Handbook, which are really, it's a collection of papers basically, and I really can, it's for free on, it's you can read it for free online. These are all scientific papers. It's not some kind of it's really a professional book, and they are all interesting. There's a lot of more in there which might be helpful. I just picked these two topics because they somehow reflected what we are currently looking for. But there's also how an auditory system or monitoring system should look like, or how it's quite recent, the book, so I can post a link later also.
And do we have chances to invite them to speak?
I don't know them. I don't know them. It's really just some kind of classical standard book, I would say, in this area. But I think can ask them if it makes sense. Why not? No?
Yeah, we might try then to keep in mind the idea. So, is there any other question, topic? I see how beautiful Europe it's becoming now. All your windows are kind of shiny. You can see light. Nice. Here it's still sunny. You can see the sun here, but it's getting colder. So, well, then I guess we can, there is a chat here. One.
It's just a link.
It's the handbook. Yeah. So I guess we can maybe terminate, and the meeting for today. I think your talk is something to be seen a couple of times. There is a lot of information.
Thank you very much.
And I think, well, that we can continue exploring this. Very, very interesting.
If you have questions, just drop me a mail. So I'm very open for email discussions. So I'm very interested in this topic. And many thanks for inviting me and having me here.
Well, no, thanks for coming. And everyone, like we continue meeting on a bi-weekly basis from now on. We had a little break for 1 week, and now we continue for one session, and now we will continue every second week. So you will get the announcement soon, as it has been going on for some months already. So I guess I'll see you again in 2 weeks, the latest. Okay.
Yes, definitely.
So,
thank
you very much.
Thank you.
Bye-bye.
Bye. See you soon.
Bye-bye.
Thank you. Bye.